And the test number 3 will be April 1st, so it's not a joke. And I will open it. It's a 1 hour test, but I will open it for 3 hours from 8 p.m. to 11 p.m. So make sure you don't have a job that day or whatever. Okay, April 1st, I think it's the Tuesday. Is it the Monday? Okay, so it will be April 2nd from 8 to 11. I will open a window. If you have any conflict, let me know and I will have to change the time. Okay, so we stopped here. And because it's so many concepts here, I made another slide here over the weekend just to review what we have learned so far. Okay, to have a summary of everything for electromagnetism. So first, we talked about static electric field. So if you have a DC circuit, then the electric field is not static. Okay, it's not electrostatic because the charges are moving. But if you have electrostatic, that means the charges are not moving. Each time you have an electric field, okay, the electric field goes from the positive charge to the negative charge. So in that case here, okay, if you have a point charge or Van Graaff generator, you see the electric field is gonna be outward, okay? Okay, it's gonna diverge. Do you agree with that? If you place a positive charge inside an electric field, it will accelerate following the electric field lines. If you have a negative charge, it will do the opposite. Okay, so we talked about voltage. So voltage is the energy per unit coulomb. So for example, here you have a Van Graaff generator. It can be charged, okay, and then it can reach a voltage, say, of 1,000 volt. That means here on the outside it's going to be 1,000 volt, inside is going to be 1,000 volt. If you touch it and if you are not connected to the ground, you will be at 1,000 volts, even though you won't be electrocuted because the current cannot flow through you if you are not connected to the ground. And even if you are connected to the ground, you're going to be shocked, but there is not enough charge to hurt you. Is that clear? So there is a voltage here. It's called an equipotential. And as you move away from the charge here, okay, the voltage will decrease as the inverse of the distance. So we already saw that. And then we talked about capacitor. So if you have two plates, one is charged positively, the other one is charged negatively, again, the electric field goes from positive charge to negative charge. Okay, so always starts with a positive charge, ends up with a negative charge. Between the plates, you see, we have a uniform electric field. Okay, and if you place a positive charge in between the plates, it will accelerate. That's how we get a particle accelerator, for example. Okay, these are capacitors. So you can read over. Okay, what else did we do? Remember that inside a conductor, there is no charge and there is no electric field. So typical conceptual equation for the final, if I try to trick you, inside the conductor, like a human being, there is no charge inside and there is no electric field after equilibrium is reached. You see this here is charged. It's an equipotential, so it will have the same potential all over. And you see that the electric field here is perpendicular to the surface. I think that was a conceptual question in test number 2. Electric field here is always showing the way for the positive charge to lose their potential energy. The electric field is trying to pull on the positive charge, so it will lower the potential energy. So we talked about the Faraday cage. So here you can have 1,000 volt or 10,000 volt. Okay, this is a solenoid. Apparently, that's what you are doing in lab, working with solenoid here. You see that can go to 10,000 volts, okay, it will be high enough voltage so there is a breakdown. Okay, so it means the electric field succeed taking the charge here, bringing it to ground, but the man here is safe. That's what is called a Faraday cage, because an electric field or charge cannot stay inside the conductor. Okay? Now, we are exposed to electric field, magnetic field all the time. It's all over around us. So, for example, even if this lamp is off, okay, let's say this is connected to 120 volt. So here it's going to be an equipotential. Everything here electric. The electric wire here will be at 120 volt, even though it's off. Okay, so what does it mean off? It means electricity is not flowing, the current is not flowing. Even though it's not flowing, you still have an electric field here because this is at an equipotential of 120 volts. So it's all over us, right? So sometimes it's good to disconnect everything. Okay, so we talk about that as well. Like, for example, how do we create X-rays? So you have a cathode here and you have an anode. So you have an electric field from plus to minus. An electron here that will be free from the wire will accelerate against the electric field. The force is Q times the voltage that you apply between the electrodes. Okay, so I'm reviewing. The acceleration will be the force, the electric force on the electron divided by the mass of the electron. Is that clear? So all that electrical energy will turn into kinetic energy for the electron. And then the electron will crash here in a heavy metal target, and all that kinetic energy will be turned into X-ray, into radiation. Okay? So we talk about that. Electric fields are used to accelerate particles. So for example, here you have a linear accelerator. And we started to talk about magnetic field. So let's review, okay, because that was a lot of information last time. Here you have a permanent magnet, okay? It's a bar magnet. For a magnet, you always have a north and a south. Okay, so it's always a dipole. You cannot have a monopole. Okay, you cannot have a magnetic charge. You can have an electric charge by itself, you can have a plus by itself, you can have a minus by itself, but you cannot have a magnetic charge. It's always a north and a south. So conceptual question, if I break a magnet in two, I still have a south and a north and a south and a north. Again, you break it in two again, still a north and a south and a north and a south. You cannot isolate a monopole. And the other thing about the magnetic field, so here we are talking about static magnetic field. So it means it does not change with time. Like before we had a static electric field, the magnetic field always like to curve, okay, to go around into a circle, which is not the same as an electric field. Electric field always start from a plus, ends up on the minus. But a magnetic field likes to circulate, okay, likes to go around. So from here you cannot see, but it's going through the magnet, out of the north, make a circle here, back to the south. Okay, so out of the north, in the south, and go through the magnet. Is that clear? Two magnets will interact with each other through their magnetic field. Okay, their magnetic field will interact with each other. So here you have north and south facing each other. So it's very much like a spring, like you stretch it out. It wants to bring things together. So that's what it's doing here. Now, if you have north and north or south and south, you see here you have no magnetic field in the center and it's repelling each other. So it's really the field interacting with each other. So if you want to visualize in 3D, you can see that the magnetic field First of all, it's a vector. Okay, so each point here, you can have a vector showing the magnetic field. I need to show you that. These are the magnetic field lines. These are the magnetic field lines. So that will be a visualization in 3D. Of course, it's not, it's just like a model. But at a given point here, if I make it right, at a given point here in space, can I make it bigger? I don't know how to make it bigger. But anyway, at a given point here, you're going to have a magnetic field. Okay, it's a vector. The notation is B. So it's going from the north into a circle here. Okay, it's the same circle. I don't know what I'm doing, and then go back. So it has to make a circle here. When you connect all these arrows here, all these vectors, you get a magnetic field lines. So magnetic field is like water flowing, but in a circle. Okay, it's going around. So likewise here you have a magnetic field vector. So it's a vector, it's going around, 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 around. It's always tangent to the line and then coming back. Is that clear? So magnetic field always comes out of the north into the south and it's going through the magnet, the bar magnet. Okay? Sometimes you have those fridge magnet, you see? So you still have a north here and a south here. And the magnetic field will be going out of the north into the south and it's making loop. So at any point here, I can have a vector that will be the vector magnetic field. Is that clear? So sometimes you have what is called a horseshoe magnet, but still it's going to go in a circle. You can visualize the magnetic field here, okay, by using iron filing. So it's little piece of iron that will rotate. So it's not going to move one place to the other, but it will rotate, okay, in such a way that it will align with the magnetic field line. And that's how you can visualize the magnetic field. Or you can have little tiny compasses that will show you so you can visualize the magnetic field line, but also the direction from the north into the south, back to the north into the south. So it likes to circulate. Is that clear? So remember that when we did that with the electric field, we were able to visualize the electric field using like little seed, tiny seed that get polarized. So it's the same idea. Um, okay, so the configuration had another here. You see now, if you go back to the electric dipole, here you have a positive charge, a negative charge. That's what an electric dipole looks like. So an electric dipole, the configuration of the electric field of an electric dipole is very much like the configuration of a bar magnet. Same thing. You have two poles, right? So it's going to be the same configuration. So we talked about that last time. What else? So you remember inside a capacitor, okay, you're going to have a uniform electric field. You see those lines, they are equally spaced. So it means the electric field is the same direction. And you even have an equation for that, right? The electric field was the voltage between the plates divided by the distance between them. Remember that from last week? Okay, so likewise, if you have a horseshoe magnet, You see, out of the north, into the south, back to the north. In between those poles here, you have about a uniform magnetic field, except if you are using a permanent magnet, we do not have an equation for it. You will have to use electromagnet. Okay, any question? So I did that, so I go over that with you. So that's when you are using your right hand rule. So this is in 1820. Okay, this is the experiment done by Ørsted. Okay, and he had this exactly that setup here. So he was doing experiment with a battery and a wire, and there was a compass sitting on the table, and the compass moved. So you see what's happening is that electricity creates magnetism. The source for magnetism is moving charge, is electricity. So if you have electricity flowing in a wire, you're going to have a magnetic field. Now it's going to circulate around the wire. So you take your right hand like this, and then where is the wire? Plus, 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 into the field. Do you agree that electricity goes into the screen for, sorry, do you see that or not? If you look at me, if you look at me, you're not going to see anything, okay? This is what it's happening. So you have the plus, 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 into the screen. Do you agree? Okay, you take your right hand. You have the right hand. Everyone has a right hand. Okay, so the thumb here, it's going to be your current carrying wire into the screen. Okay, so the magnetic field is going to rotate which way? Clockwise or counterclockwise? Clockwise. Very good. Okay, so that means every point here you will have a magnetic field vector going this way. Do you agree? You go from the plus into the screen, so it's going to be clockwise. Do you agree? So you see that here. Can you see that? So usually you always talk only about the segment of the wire. Do you see the segment of the wire here? Okay, so that the power supply plus and minus, which one is the current? Thumb is the current, so it's going this way, right? So that's the magnetic field. Do you understand? So it's going to circulate in this direction. Close to it, it's going to be very strong magnetic field. As you move away, it's going to decrease in magnitude as 1 over the distance. So that's why it looks like a contour line. You see, very close to the wire, the magnetic field is going to be very strong. As you move away, you see the space between the lines increases. That's because the magnetic field gets weaker. Is that clear? You can see that if you place a compass here, it's going to show you which way it's going to rotate, right? So because that will be the north, that will be the south, okay? So magnetic field always go from north into the south. Do you see that? From north into the south. Do you agree? So that's a very famous experiment that was showing that electricity or a moving charge creates or generates a magnetic field. You can see that here. You have the wire here. Yes, the wire. Do you see the wire on this one? The current goes up. Do you agree? So magnetic field will be rotating this way. Okay, that's called the right hand rule. Everyone, do you understand? Okay. That's Ørsted experiment. And then we talked about, so that will be the configuration for a bar magnet, out of the north into the south. Magnetic field always like to circulate. And likewise, the Earth behaves like a bar magnet. So it means the magnetic north is at the south, and the magnetic south is at the geographic north. Okay, So that's why if you have a compass here, the north of the compass will be attracted to the south, the magnetic south. So it's showing you the geographic north. Is that clear? So why is that happening? Because inside it's like a dynamo. So in the outer core of the Earth, you have like moving charges, right? It's iron. It's so if you're interested, you can look it up here. So the inner core is solid because all the pressure, but the outer core is liquid, and you have like ions, charged particles moving. So it's like a dynamo. So it's gonna make no, it's just gonna make a magnetic field, like a bar magnet. Okay? Uh, okay. Oh, and then here, if you have a solenoid, so let's go back to my app. So just to review what we did last time, but it was a lot of concepts, so that's why I'm going over them. Especially if you are in biology, you have to deal a lot with magnetism and electrostatics. Just if you want, can you open? You're not willing to open? Yeah.
So the geographic north will show us south of magnet or opposite of something when it comes to the Earth, and then the geographic south will show you north.
North, exactly. So if I have here, you see the geographic north is the magnetic south. So if you have a compass, that will be the north, that will be the south. So it's just a magnet as well. So of course it's going to be attracted to the magnetic south. That happens to be the geographic north. Okay? Oh, here it is. Um, okay, so now if you take that wire, very, very, very long wire with electricity flowing through it, and you wrap it like this, like around a cylinder, you make it like a cylinder shape, what you're gonna get? You're gonna get something like this, right? So if you have a solenoid, the magnetic field will be exactly like a bar magnet. Okay, so that's why this is called an electromagnet. That's how you have electromagnet. So if you have solenoid, again, you take your right hand, okay? So the electricity is going from plus to minus, yes? So it's going to flow this way, okay? The thumb will show you the north. Okay, so it's something different. I'm still using my right hand rule, but it's not for the same purpose. So now you have electricity flowing. You see that? So that means the thumb this way. That's going to be the north. And here, that will be the south. Do you understand, or I have to show you on the screen? I, I cannot move too much, right? So you have plus, and then it goes around, back to minus. So if you take your right hand, okay, you go around like this, the thumb will be the north. Okay, so this is called an electromagnet, and it will behave like a bar magnet. That will be the north, and that will be the south. Very good. Okay, like I told you, if you want to for a demo make an electromagnet, they are very easy to make. Yeah, a lot of tutorial online, and proof. You see. That side will be the so very good. And if you go on the other side, you see that's gonna be the north. Okay, so you take you have your solenoid. You take your right hand. If the current is flowing this way, that will be the north of your magnet, and that will be the south. See how it works? And you can follow, you see, a compass always will align itself with the magnetic field line. Okay, so it means the magnetic field will flow here from the north into the south, from the north into the south. Is that clear? Now, if you want to improve your magnet, inside here, you will shove inside a core, okay, made of soft iron. And what it does, okay, it will squeeze all the magnetic field line and squeeze it inside the core. So you amplify the magnetism. Because if you leave it like this, you see it's not going to be strong here. So you don't have yourself a very strong magnet. So what they do, they put like a core inside. So it will squeeze all the magnetic field so it doesn't leak out, and it increases the magnetism. Okay? So this is called an electromagnet. You see? Easy to do. You have a power supply. It's going to flow from plus here to minus. And you have yourself a bar magnet. One side will be north, the other side will be south. Inside, you shove like a piece of iron, and that will amplify the magnetism. Okay, it will make it stronger. You can visualize again, here you have your solenoid, and that's a demo I used to do. So you have a iron filing that sprinkle all over. You can visualize the magnetic field lines. Same thing here. Okay, so if you have a loop of current, okay, you go around like this. That will be your north, and that will be your south. So each time you have a loop of current, like if I have time, I will do this demo. I hope, because it's very heavy, so I don't want to have to carry it again. So you see, I have a loop here. It's a coil. It's a small solenoid. If you want, it's a loop of current. So if I connect that to a power supply, you see the current is going to flow. If it's flowing this way, that will become the north, and that will become the south. So it will behave like a bar magnet. Is that clear? Okay, so lot of application. Here you have a very strong electromagnet. It's used for MRI. Okay, MRI, they use a huge magnet, very, very dangerous. To move junks around, you have an electromagnet. And again, you see, current is flowing this way. So north will be that way and south will be this way. So each time you have a loop of current here, okay, from plus to minus, you take your right hand, you follow the direction of the current, and the thumb will be the north. So the thing to understand is that the source of magnetism is moving charges, is electricity. So that's why it's called electromagnetism. Okay? You can have, like the capacitor, you can produce, you can generate a uniform magnetic field if you have two coils. Okay, this configuration is called Helmholtz coil. Okay, so you have two coils and you connect that to a power supply. And for a given geometry, so it means that the distance between them has to be equals to the radius. Okay, so if you do that, in between, you're going to have a uniform magnetic field. So you see the symmetry between electrostatic and magnetism. The same way that if you have a capacitor, you're going to have a uniform electric field. If you have two coils like this, in between, you're going to have yourself a uniform magnetic field, and there is an equation for that. So you can do all kinds of experiments, especially in biology, if you're doing research. So you see here magnetic field always circulate. Okay? Electric field, when it's electrostatic, diverge or converge. Magnetic field, static magnetic field, always like to circulate. Is that clear? So imagine to what we are exposed all the time. If it's off, you still have an electric field because here you have a equipotential 120 volts. So you're going to have an electric field here, static electric field diverging away. And now if it's on, now you have electricity flowing, and now you're going to have magnetic field as well. Not only you're going to have a magnetic field and electric field. So it's all over us, right? We cannot see it, but it's there. Is that clear? Okay. And then that was a little bit challenging to understand. But if you have a current, okay, so it's a wire carrying current, so a wire with a current flowing through it, and you place that wire inside a magnetic field, the piece of the wire that is inside the magnetic field will be acted upon by a magnetic force. Remember that? And that's what when you take your height. Okay, let me show you a different way to do it. Can you take your 3 fingers like this? Okay, so that like that. Make like this, right? Okay. So if this is I, if this is the current, and if this is B, that will be the force. Okay. So it means if the current is flowing through that wire, and it's inside a magnetic field, you see, it's both of them make a plane. So this is a plane, I, B. So the force will be perpendicular to the plane. Okay, so it's like X, Y, Z. This is the current, this is the magnetic field, and that will be the force. Okay, you see the current and the magnetic field are in the same plane. Okay, it's flat. Do you understand? And that will be the deflecting force, the magnetic force. Now, the current and the magnetic field, they don't have to be perpendicular to each other. Okay, they can make an angle with each other. So that's fine. You still have a force in this direction. If the current and the magnetic field are parallel to each other, there will be no force. So you need a component perpendicular to the magnetic field. So let's do this one. The first one, take your 3 fingers. Maybe it's easier with you can do it with your hand. Okay, it depends. But let's try to do it with your 3 fingers. The current is this way. Current is this way, yes? The magnetic field from north to south. So this is north, this is south, yes? So the current goes this way, magnetic field goes that way, the force will be up. Do you understand? So always IB in the same plane, the force in a perpendicular to both, perpendicular to the plane. Is that clear? Now, if the current is flowing in the opposite direction, so the current is towards you, magnetic field is in the screen, the force is down. I, B, F. So now you can go on, you say I, B, F, I, B, F, I, B in the same plane, F perpendicular to both. I, B, F. Okay? What about here? What do you think? Think about this one. So no magnetic field from north to south. The current goes in. So it has to be perpendicular to both, right? So it has to be one or the other, right? So take your 3 fingers. I is inside the screen, yes? B is out. So again, yeah. Okay. The current is inside the screen, yes?
Yes. Yes.
Magnetic field is up. So which way is the force?
To the right.
To the right. You see? I, B, F. Is that clear? So it will be deflected to the right. So here you see it again. Look. Here you have a piece of wire. The length is L. Okay? The magnetic field is in this direction. So you have I, and then you have B, I, B. So already you see that it makes a plane. So the force has to be up or down. But if you do X, Y, Z, so it's going to be up. Okay? Is that clear? This one is a nice slide. Okay? So take your three fingers. It's good for flexibility, okay? Let's do yoga together. I, B, F. Okay? It's called the right hand rule. You can do it this way as well, but you see that I and B are in the same plane. Okay, maybe this way is easier for you. F comes from the palm. I, B, F. I, B in the same plane. F is perpendicular. Do you agree? Okay. And that will do coming next. So I just want to show you. I know if it's going to work, but here is another experiment that you could do. Let's see. Okay, so I have a power supply. Is aluminum a conductor? Yes. It's a conductor. So I'm going to do a short. So I cannot do that a long time because it's going to get very hot. It has a small resistance here. So all the energy is going to turn into heat. And here I have a magnet. So if I tell you the truth, I should be able to move it with the magnet, okay? Let's see. Not long. Ready? Ooh, I'm making spark. Ooh, ooh. Do you see that? Wow, isn't that amazing? Do you see? See? So you see that the current is going this way. The magnetic field is going that way. So the force has to be this way because they have to be X, Y, Z perpendicular to each other. You see, because this is a magnet, this is north here, and the other, this is south. So if I do this, you have magnetic field in, the current this way, so the force has to be in this direction. Isn't that cool or what?
Oh wait, I'm having that challenge. It's a rare. Oh yeah, like this, like yeah. I'm like,
but it moved. Maybe I killed my power supply. But you saw it happening, right? Okay, so I just have another R, and then we go back to the math. So you see here, the current is flowing, so it's going to be towards you. Okay, so the electricity is towards you. Magnetic field is this way. So where do you think it's going to go? This way or that way? So if I ask you that for conceptual question, poof, this way. You see that? Right? You can do your three fingers. The current is towards you. Magnetic field is down. So the force is sideways. Do you see?
force be with you.
Yeah, the force Let it be with you. So only the force is acting only on the segment that is placed in the magnetic field, only in here. Now if I reverse the current, it's gonna go the other way. Isn't that cool? So let's see if I didn't kill my power supply. Aye, aye, aye. Aye, aye. So you see here I have a horseshoe magnet, okay? And here, what you have to understand is that the force will be applied only of the bit of wire inside the magnetic field. So where is the magnetic field? From up to down or down to up or sideways? This is the north, this is the south. So the magnetic field is, so it's going to be down. Electricity will flow this way, right? Yes, very good. So the force will have to be sideways. Do you agree? Okay, the current, the magnetic field, the force. So let's see if I can make it move. I don't know if it's going to work because the magnet is not very strong. Can you not move, please? Well, it's supposed to move. I think but you get the idea, okay? I think I killed my power supply. Okay? So remember we did that last time? Take your 3 fingers for the last time. The current is going into the screen, okay? The current is in the screen. B is sideways from north to south. So you see the force will be down. You see that? It will do something like this. Okay? The current is this way, magnetic field is that way, the force will be down. Okay? Or you can do it this way, it works as well. So if you have the current flowing in the opposite direction, the deflecting force will be up. Okay, now let's do the math. So magnetic field here from north to south, and then you have a piece of wire, so the length equals L. That will be the wire carrying current inside the magnetic field. And then you have a magnetic field B, and you will have the deflecting force. And that sine, that angle here, will be the angle between the current and B. So if you have the current here and you have the B, they don't have to be perpendicular to each other, but the force will be always perpendicular to I and B at the same time. If the I and B are parallel to each other, what's going to be the angle between them? 0. Do you agree? Sine of 0 is sine of 0 is sine of 0 is no, sine of 0 is 0. So there is no force. Okay? If they are perpendicular to each other, if the current and B are perpendicular to each other, the sine of 90 degrees is 1. So the force will be perpendicular. And look at that. Can you all look like some people over there are doing something else? Over there. Hello. All the way. Cora. She's hello. Okay? So if it's perpendicular, they're going to be maximum. As you decrease the angle, the force is going to decrease. When they are parallel to each other, there is no force anymore. See how it works? So the magnitude, so we're going to do some problem, but the magnitude of the force, the magnetic force will be the current flowing through the wire. The length of the wire inside the magnetic field, and the sign between the current and the magnetic field. Okay, so I is the current, L is the length of the wire, B is the magnetic field. The angle here is the angle between I and B, and F is the force. If the angle is 0, what's going to happen to the force is going to be 0. Okay, like this, 0. As you increase the angle, the force is going to increase, and when it's perpendicular, the force is maximum. Do you agree? You see the current and B, they make a plane together, and the force is perpendicular to both. Okay, so here again, if you want to practice, the current is toward you, magnetic field is down, so the force will be in this direction. Okay, so I will have that on test 3, because even if people can cheat online, those type of conceptual questions, it's very hard to find the answers online. So make sure you know how to do it. So what do you think here? Again, the current is up. Okay, B is in the screen. Where is the force? Very good. To the left. Right? Yes. This one is always I, this one is always B, this one is F. And then you have to do some yoga. So here it's up. I is up. B is in the screen because you have cross. The crosses means it's in the screen. And then you open the last finger, that's going to be to the left. Yeah. Okay, so I, start with I. I is toward you. This way. I was looking at that. And then B is from north to south, so it's down. So you have to rotate your wrist to do B down. Okay? And then you open your last finger, so that will be to the right. I is towards you. B is down. So that will be the force F to the right. Right? It has to be X, Y, Z. Okay? So X, Y, Z.
Are there gonna be like word problems?
No, the problem will be, okay, you have the north and the south, you have the current, which way it's going to be deflected. Okay, so what do you think here? The B is in the screen, the current is towards you. Do they make an angle with each other? No. So you don't have to torture your hand. That means the force will be 0. Okay? If I and B don't make an angle with each other, there is no force. What about B? So B, they are toward you, B is toward you, the current is toward you. Is there any force? No. So let's find C. Where is the magnetic force? So the current is the current is, no, the current is like the little circle. So the circle means toward you, a cross means in the screen. A circle means out of the screen, a cross means in the screen. So the current is, was it how? So the current is toward you, right? Magnetic field is left. So what is the force?
Down.
Down. Very good. Very good. Okay? Yeah. So the next one is the opposite, right? It's towards you. So the force will be up. So this one is down. gravity is down. So can you support the wire? No. In that case, the magnetic force is up, the gravity is down. Can you support the wire? Yes. So the answer is D. Okay? Yeah.
Sing again one more time, right?
This one?
Yeah.
So that means the current is towards you. So that means the current is towards you, the magnetic field is away from you. They are parallel to each other, so there is no force. If the current is parallel to the magnetic field, there is no force. This one, the current is towards you, the magnetic field is towards you, still no force because they are parallel to each other. The second one, you have to take your hand. The current is towards you. The magnetic field is this way, so the force will be down. And gravity, so it's like a wire, so it will be deflected down, and gravity will pull it down, so you cannot have an equilibrium. The D will be the opposite, right? So the magnetic field will be up, gravity will be down, so it's all good. So the unit for magnetic field is the Tesla, okay, named after Tesla. And one other unit, sometimes it's called the Gauss. And 1 Tesla is 10,000 Gauss. Okay, so now you can help each other and do the math. Okay, so always think the current, the magnetic field, and the force, like this, X, Y, Z. You just have to be able to do something like this, like that, it's like a workout. Okay, let's try to do this. Do it, do it, do it, do it. Okay, I'm gonna bring my slide here because it's a very nice slide here. Are you doing it? I'm gonna put that on the side somewhere. Okay. So what's the equation for the magnetic field in magnitude? It's gonna be the current flowing in the wire times the wire length, the length of the wire inside the magnetic field times the magnetic field times the sine of the angle between B and I. Okay? The magnitude is in Newton. The current is in amp. The length is in meters. Magnetic field is in Tesla. Okay? And the angle here, the angle is the angle between the current and B. So you see that if the angle equals 0, force equals 0. If the angle is 90 degrees, the force will be maximum. Okay, so can you do it? So the length is needed. The length is in meters. So what does it say here? First of all, you identify the physical quantity. You see it's Newton. So that means it's going to be a magnetic force. Here, you have the current because amps. So that will be 12 amp. Okay, that will be your current. That's going to be the force. Here they give you the length of the wire placed inside the magnetic field. So you don't need the whole wire, right? Like here you have a power supply somewhere, plus or minus, and only this part is inside the magnetic field. So here L, that's a L equals 0.30 meters. Okay? What's the equation? Find B. Okay, so you are using this equation here. Okay, so that's not hard, right? So the magnetic force equals the current, okay, times the length of the wire inside the magnetic field times the magnetic field times the sine, and it's perpendicular, so it's going to be sine 90. The wire is perpendicular to B. Okay, so now you just have to plug it in. So 2.4
What are the units of the magnetic?
Tesla. So 12 times 0.3 times B, and you see the current is perpendicular to B. Okay, the current here is perpendicular to B, so that will be 1. So B will be equals to
8.64.
6. Did you all do it? So you do 2.4 times 10 to the negative 4 enter, divide by 12, enter, divide by 0.3. So what do you get?
6.67.
Times 10 to the negative
5.
5. Tesla. And if you have to convert to Gauss, okay? So one Gauss, it's another unit for magnetic field, will be equals to 10 to the negative 4 Tesla. So how can you convert to Gauss? How do you do that? You divide because you want to know how many times 10 to the negative 4 Tesla goes into that number. Okay? Or you can say 1 Gauss is 10 to the negative 4 Tesla. So if you have 6.7 times 10 to the negative 5 Tesla, how many Gauss you're going to have? You divide. So magnetic field will be equals to, so you divide this by that. So it's going to be about 0.7 Gauss. Do you agree? So the Earth magnetic field is about 0.5 Gauss. So it's a small magnetic field. Any question? Okay, so once we survive this torture with the hand, and then it's easy. The math is not hard. Let's do number 2. So you always say a wire carrying current. A wire carrying current. That's the terminology. I stop. Okay, so F equals ILB, the sine, and here you have the angle between I and B. I is the current. It has a direction. It goes from the plus to the minus of the power supply. So first of all, you identify the physical quantity. So that's the current. Has a length of, that's going to be your wire, the length of the wire. Okay, then that will be the first thing you want to do. Okay, you identify the physical quantity and you convert that to the right unit. So 40 milli, when you see milli, it means 10 to the negative 3 Tesla. Each time you see milli, you substitute by 10 to the negative 3. If the wire is perpendicular to the field, so that means that angle here is 90 degrees, how much force? So F question mark. You see? So it's not hard. So force equals I, so 1.5 times 0.2 times 40 times 10 to the negative 3, and it's perpendicular. The wire is perpendicular to the field. So that angle here is 90 degrees. So here is the angle theta. And you get, are you doing it? So in scientific notation, 1.5 times 0.2 times 4, is that 40? 40 times 10 to the negative 3. Uh, what did you get?
0.012.
0.012, which is 1, 2. So 1.2 times 10 to the negative 2 Newton. Did you all get that? Okay. Okay. Okay, let's do number 3. Okay, let's try to do a drawing. So the force here, question mark, for the direction magnitude of the force, upward magnetic field. Okay, so I'm going to make a magnetic field up. So if I do it properly, which I didn't, you see those vectors, they should be equally spaced because it does not change in magnitude. So that will be your magnetic field. And the current, so I'm going to make the current going this way. Maybe here you're going to have a power supply. Okay? So the force should be, you see, perpendicular, right? So it should be in the screen or out of the screen. Do you agree with that? Because it has to make a X, Y, Z. So what do you think the force is? In the screen or towards you? Take your free finger. I, B, F. So the force is?
Oh wait, I'm doing it with my left hand.
I know it doesn't work with the left. You can do it with your left, but whatever you find, you opposite. So
Left hand.
the current B. So the force is towards you. Towards you. I, B, F. So towards you. So, okay, so now you can do the math. The force is towards you. That means towards you. So, I, B, F. Okay, so let's go back. What in now? So F, that's what we are trying to find. Okay, you have the magnetic field here. You see? B, E is 2 milli means 10 to the negative 3 Tesla. And the current is 10 amp. And length is 0.15 meters. And the angle between them is 90 degrees. You see? This here is 90 degrees. It's a 90 degrees angle. So you have the force equals ILB, the sine of the angle. Hmm? Yeah, no, milli means 10 to the negative 3. So it is Tesla, but there is a milli. Milli means 10 to the negative 3 times 2 times 10 to the negative 3 sine 90. Because the angle between I and B is 90 degrees. So 10 times ta 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 sine 90. So that's going to be okay. So that will be 3 times 10 to the negative 3 Newton. Or 3 milli Newton. I don't know if we say milli Newton, but it's 3 times 10 to the negative 3 Newton. Okay? Everyone is on board? A lot of people didn't wake up at all with the time shift. I don't know.
My brain is like, what?
It's useless. I really do not understand why they do that.
There, I should phase it out.
They no, it doesn't make sense. Especially in Florida, it's not like we have a big winter and a big summer. You know.
We have second conference thing.
It's just for students to fail their exam that they do that. Number 4. L'un, perpendicular to Earth magnetic field. That will be the force. Perpendicular to Earth magnetic field. So the angle is 90 degrees. And that will be the magnetic field of the Earth, okay, which is 0.5 Gauss, which is 5 times 10 to the negative 5 Tesla. What's the current? So if you have a strong enough current, if the current is strong enough, you can have the magnetic field of the Earth deflect that current. But because the magnetic field of the Earth is so small, you really need a very, very strong current, like crazy strong. So 0.112 equals 0.8 times 5 times 10 to the negative 5 times the current. What else do we have? That's it. Sine 90. So what do you get?
I don't know if anyone else got this, but I got 3,000.
Yeah, about 3,000. 3,000?
Something wrong. Well, I put let me try now. 1,000.
Okay, maybe I did something wrong then. 0.8 divided by 5. 3,000. I don't know where you got your hundreds.
Me neither. Maybe I mean this is not my calculator, so maybe I put something wrong.
But you see uh, the Earth has a magnetic field. I don't know if you can see here. At that latitude of Florida, you see the magnetic field goes here. Higher altitude, the magnetic field goes into the Earth. Do you see here? Isn't that interesting? It's interesting because in all those birds, they have like a compass in their heads. You see the magnetic field here goes in at that latitude B. That's gonna be B. And here, Florida, it's about like this. And at the equator, it's gonna be like this. You see, so you can use the magnetic field of the Earth to do experiments. Are you with me? Okay, number 5. 3,000 amps. 3,000 amps, which is huge. Huge, huge, huge. I don't know how to get 1,000. 3,000 amps. Okay. So let's draw. So you have a wire. Okay, that will be the length. And you have a current I. And you have its weight. So that will be the weight. So it means that you have a wire like this in mid-air. Okay, so you're holding your wire like this. And you want to know if you can let go. So what's going to happen if you let go? You have gravity pulling down. Do you agree with that? So that will be 0.35 Newton. Okay? And you have electricity flowing in this direction. So we want to find a magnetic field strong enough to balance it, right? So how much should be the magnetic force if you want to balance the wire? So I have a wire like this. You have current flowing. Gravity want to bring it down, obviously. And I don't want it to go down. So I have to balance it by a magnetic force. Same value, but up, up, right? Yes. The weight is in Newton, yes. The weight is gravity. The force due to gravity is in Newton. It's a force, right? It's the pull due to the Earth. So that will be the magnetic force. Okay? Okay, so let's find, I don't know what's the question. The magnetic field. Let's find the magnetic field. Which way the magnetic field has to go? Take your free finger.
So this is
I, B, F. So I is this way. Where is B? So F is up.
right.
So I is to the right. B I decay, but I know that B is the force is up. So
Oh, we're not using the weight.
It's gonna be in the screen. I, B, F. So the magnetic field has to be in the screen. Okay? Toward the screen. And so let's find the force equals ILB and the angle between I and B. Do we have the magnitude of the force? Yes, because they balance each other. So it's like you have your wire, gravity is pulling it down, magnetic force is pulling up, so they're gonna balance each other. So you have, what's the force here? It's gonna be 0.35 equals 6 times the length is 0.4 times B times sine 90. I. And you are solving for B. Ay. My back. It's okay. Ah, thank you so much. What's your name?
Nathan.
Nathan. Ah, you are the other Nathan because I have another Nathan here. Same name. I have like 2 or 3 Rachel. I have one Rachel. Is there another Rachel here? No? So what's gonna be B? What did you find?
I mean, I don't know. Maybe it's not the reason like cake. But I got 2.6 something.
Huh?
1
One point something?
45.
Oh, it's me then. 0.35 divided by 6 divided by 0.4. Okay, you're right.
What I got?
1.46 Tesla.
I know. Why do you have it as 1.46?
Huh?
Why do you have it as 1.46?
I don't know. Because I round 1.46. Oh, thank you. Yeah. Yeah, there is a point here.
Yes.
Okay. Okay, do you agree? Let's move on. No? What you don't agree with? Hmm? Got it? So I, B, F. I, B, F. So application, each time you have electric wire placed in the magnetic field, okay, the wire will be acted upon by a magnetic force. So inside the speaker, you have a wire and then going around and then going around, going around. So it's like you have an electromagnet. Okay? When electricity is going to flow, the permanent magnet is going to push and pull on the coil with the same frequency as the sound. So if you make is someone musician? How do you make a A4 middle C? A above middle C, A4. You know the frequency that you use to tune a piano? You don't know? Like 440 hertz. It's a sound. It's a pure sound. Oh, anyway, you have a music coming here, so it's got the electricity is going to flow at the same frequency as the music. So that electromagnet here is going to be pushed and pulled at the same frequency. That's how you're going to make sound wave. Okay, so I have a demo, but I don't know if my power supply is still alive. That's the makeup. Makeup are always hard. Okay. So that's a speaker. Do you agree that it's a speaker? And do you see you have a magnet here? Do you see the magnet? All around, it's a permanent magnet that you have around. If you look inside, maybe it's a demo for you that you can do. Speakers are very cheap. You can buy them online, or you can, take apart your other speaker so it won't be that noisy. You see how it can move? Okay, so if it's moving at a given frequency, that will be the frequency of the sound that you are making. And the current here will flow at the same frequency. So if I make, for example, A4 that you use to tune piano, for example, A4, so the current is going to flow at a frequency of 440 hertz. That's going to push and pull at a frequency of 440 hertz. It's going to push and pull the air. So you're going to have a sound wave with the same frequency. What I want to show you is that if my power supply is not dead, okay, you should see, if it's not dead, you should see that if I touch here, I killed my power supply. I cannot believe that. Oh no! Oh no! It's dead. You see, I did a shot and I killed it. Make me very sad. I have a backup. I have a backup here. Okay, so that's a power supply. And let's see if it works. You see? Does it move? You see that? Isn't that cool? So if I do it at a high frequency, I can make a sound, but I cannot go fast enough because to make a A4, for example, above middle C or something like this, it has to be 440 hertz. So it means up and down 40 and 440 times per second. So I go, then I will make a sound. Isn't that cool? So maybe with this, I think I'm gonna throw it in the. That's it. It's there. So maybe it's gonna work with this now. Okay, let's see. Ready? No, it doesn't work. Let's say it works, right? I have to be exactly here. Oh, do you see it? Some people were not watching. Look, look. Oh, do you see that? So it works. So I killed my 6-volt battery. Okay, so anyway, so you have here a permanent magnet, and you have here around one wire, two going around, three going around, and so forth and so on. So when you're going to compute the magnetic force, you need to take into account a number of loops. Okay, so this is how it works. You have a magnetic field from the permanent magnet, and you have a wire going once and twice and three times and four times and so forth and so on. So you're going to have a magnetic force. Either it's pushing out or it's pulling in. If you take your 3 fingers, you see here, the current is in the screen, magnetic field is up, so the force is this way. Okay, I, B, F. Are you with me? Okay, let's compute. Let's do the computation for the magnetic force. So when you have a speaker, you will have to do F will be equals to the number of loop times the length of the wire times B, and the angle is 90 degrees. But what is the angle, the length of the wire? Because it's going around. So what's the length of a wire that goes around, that make a circle? 2, what's the distance around the circle? 2 pi r. Okay, so the force, the magnetic force in that case will be equals to the number of loop times the length of each loop, so 2 pi r times b. Okay. Because you see, you go once, and then you have a force on this loop, and then a force on that loop, and then a force on this loop, and then a force on that loop, and then a force on that loop. That's why you have to multiply by the number of loops. So the forces add up. That will be the length of a loop, 2 pi r. Okay? So 2r is just the diameter, okay? So this is 2r. That will be the number of loops, and that will be your B. So that if you want to go into more details, that slide comes from the textbook Johnson and Cutnell, the one that I recommend if you want to take the MCAT, for example. They have beautiful examples. Solve problem. Okay, so 2, can you do it? So number of turns, so 55 times. So this is the circumference. Circumference means 2r times pi. 2r is the diameter times pi, right? Do you agree? The distance around is 2 pi r, so it's going to be 0.0025 times pi. And then I'm missing the 0.1. Oh, and I'm missing the current. Look at that. I forgot the current. 2. So what do you get? Yeah. Okay. So I invite you to open your textbook, Johnson and Cutnell, even if it's an older edition. That slide comes from that book. Okay. So it means it's going around. You see, that piece of wire will be experiencing a force. That piece of wire will be experiencing a force. That piece of wire will be experiencing a force. So that's why you need to add all the loops together. So each loop experiences a force. So that's why you need to multiply by 55. And one loop, the length of a loop, it's the length, it's the distance around the circle. Okay, it's 2 pi r. Is that clear? Right?
One loop, 2 pi r, one loop.
One loop, one distance around is 2 pi r. And you go around one loop, and then another loop, and then another loop, and then another loop. So each loop here is experiencing a force because of the magnetic field. Okay, so you have the magnetic field up, magnetic field is up, up, up. That will be the magnetic field. So each loop is experiencing a force, a force, a force, a force. So it adds up. So N will be the number of loops because that will be this force plus this force plus this force plus this force. So that will be the magnetic force because each loop is experiencing a force inside the magnetic field. So you go loop and loop and loop and loop and loop and loop. Okay? So, oh, it's 3:30, but how can we find the acceleration? Some people have forgotten that for the test number 2, F equals ma. Acceleration is the force divided by the mass. So in that case, it will be 0.086 divided by 0.02. That's going to be your acceleration. Okay? So make sure that before Thursday, I know you are tired because the change of time, it's not cool at all. But make sure you open your textbook. You go to magnetism, magnetic field, and you will find exactly the same slide and go over the textbook, okay? Otherwise, it's not that easy to digest. It's not that intuitive because it's not like we see the magnetic field and we see the magnetic force.